All right, today's video is or today's lesson is on learning target 4 and 5, and there's basically two words that we're going to talk about today: the word and the word or. We're going to be doing multiple probabilities, and it's going to either say something like find the probability of this and that. It's going to be find the probability of this or that. Learning target 4 is the and. Learning target 5 is the or. All right. So let's take a look at 4. Calculate the probability of dependent and independent events. And is multiply. You'll know a little bit more, you'll understand a little bit more about what that means as we do some more problems, but and is multiply. It has a formula. The probability of A and B is always the probability of A times the probability of B, regardless of if it's an independent or dependent event. So the first two questions are just kind of warm-ups. Find the probability using the formula. Find the probability of A and B if you're given the probability of A is 1/6 and B is 1/6. Formula says do what? Just multiply them, right? So 1/6 times 1/6 gives you 1/36. Pull up the calculator. 1 divided by 36 gives you about 2.76%. About 2.7%. 2.76. All right, so then number 2, again, still just a little warm-up. The probability of A and B, given that A is 2/5 and the probability of B is 2/3. Again, multiply. 2/5 times 2/3 gives you 4/15. That fraction doesn't reduce. And that's approximately, let's see, 4 divided by 15, 26.67%. 26.67%. So some of the questions in the homework quiz test, they require you to know the formula. Because right now you're like, what's A? What's B? Well, we're about to do some work where we define the A, and do that same formula. All right, but before we do those, here's a quick reminder. What's the difference in independent and dependent? First bullet. If you're counting the number of 2-digit codes that are possible, is that an independent or dependent event? Well, think of it this way. When you pick your first number on that code that you're going to make, when you pick the first number, does it affect the next choice? If you say the first number is 5, does it have any influence on your second choice? No, so then those are independent events. This isn't an order matters, okay? Don't get that confused. It's not an order matters question. It's does the second choice depend on the first? All right, the second bullet. When you choose meat, bread, and toppings for a sandwich, when you choose your meat and then go to choose the bread, does it affect the second choice? Does choosing a bread or choosing a meat affect the second choice? No, you're right, it doesn't. So it's independent as well. What about a license plate with 2 letters followed by 3 numbers if repeats are not allowed? Think about that one. If you choose the letter A as your first letter, does that affect your second choice? If repeats aren't allowed, then you can't use A again, right? So that means that your second choice depends on the first. It depends on what you pick first. So the first 2 were independent. The second one, dependent. All right. Now let's do some actual probabilities. At a picnic, there were 10 diet drinks and 5 regular drinks. There are also 8 bags of fat-free chips and 12 bags of regular chips. If you grab a drink and a bag of chips without looking, what's the probability that you get a diet drink and a fat-free chip? It doesn't matter if they're independent or dependent. You're still going to multiply their probabilities. But when I grab a drink and I grab a chip, does my drink influence what chip I get? Or are those like separate choices? They're separate. They don't depend. But the probabilities would be the probability of a diet times the probability of getting fat-free. Well, what is the probability of getting a diet drink? 10 out of 15. Perfect. Probability of getting a fat-free chip? Yeah, 8 out of 20. So we could reduce these in our head and multiply, but we'll just grab the calculator. 10 divided by 15 times 8 divided by 20. Enter, math, enter. So 4 out of 15, 26.67%. Not too bad, right? It's basically doing 2 of what you did yesterday in Learning Target 3. But the words and between them, so you multiply. All right, now we're going to move into the 52 card deck. So as I said a couple days ago, if you don't know your deck of cards, you need to make a note card, make a list somewhere. What's in a deck of cards? See, what are the suits? Hearts, diamonds, which are both red, by the way. Hearts and diamonds are both red. Spades and clubs are both black cards, right? All right, what are the numbers on the cards? Okay, good. You said 2 through 10. Notice you didn't say 1. There's not a number 1, right? There's a 2 through 10. Ace, jack, queen, king. So there's 13 numbers. If you don't know that, make a note somewhere because we're going to be doing a lot of probabilities with cards. All right, number 4. If you draw a card out of that 52 card deck, no jokers, never jokers, and then replace it, and that's key, you replace it, and draw another card, find the probability that it's heart, comma, then black card. Well, first of all, would you put the word and or in between? Think about it. Heart and then black card, heart or then black card. Which one sounds right? It doesn't sound right to say or, does it? So this is an and, so it's a multiplication. Yeah? So we take these separately, though. Remember, the probability A is a heart, B is a black card. So what's the probability of A, the probability of a heart? 13 out of 52. Some of you may reason it out that it's 1 out of 4. And you're right, because there's one of the 4 suits. 13 out of 52 reduces to 1/4. What about a black card? How many out of 52? Yeah, 26, half the deck, 26 out of 52. So speaking of those 2 reduced fractions, the first one reduces to 1/4. The second one's 1/2. So what is 1/4 times 1/2? 1/8. And that's 12.5%. All right, you do number 5. A is the probability of getting a jack. B is the probability of getting another jack. So 4 jacks, right? All right, so 4. And why is the second fraction 4? Because you put it back. You put it back, you replace it. So 4 out of 52 times 4 out of 52. Okay, and that's, you're exactly right. That replace it phrase is why the second fraction is still 4. Okay? So that's 1 out of 13 times 1 out of 13, which is 1 out of 169, or approximately, let's see, that decimal 1 divided by 169, 0.0059. I'd call that 0.6%. About 0.6, 0.6%. So what changes in 6 and 7? Read the directions. What's different in 6 and 7? You don't replace it. When you don't put it back, it kind of depends on what you drew first. Does that feel natural to say? If you don't put it back, kind of depends on what you put on what you drew the first time. These are dependent events. All right, so let's take a look now at number 6, the probability of getting a heart and then a red card. All right, let's start with the heart. 13 out of 52. Now be careful. The second fraction, you don't put it back. So you grab a heart, set it to the side. How many cards are in the deck now? 51. Be very careful. How many red cards? Good, you said 25. Why not 26? Because you put one of the reds to the side. Very good. Good catch. 25. Yes, there's 13 diamonds, 13 hearts. So there's 26 red cards. There's 26 of those. Half of the deck is red, half of the deck is black. So grab the calculator for these fractions. 13 out of 52, which we could have typed 1/4, times 25 out of 51, enter, math, enter. That is about 12.3% and a fraction of 25 over 204. 25 out of 204, about, oh, and it does that. Sometimes when I write the 4, it connects the top and makes a 9. I still haven't figured that out. So let's try that 4 again. All right. About 12 point, what'd I say? Yeah, 12.25, 12.3%. All right, you do 7 then. Probability of a jack and then a king. So it's multiplication and 2 fractions. So jack first. What are you thinking? 4 jacks out of 52. Good. What are you thinking on the next one? Why 51? Because you didn't put it back. Good catch. It's 4. See the do not replace it? If you literally draw a jack out of the deck and you set it to the side, there's only 51 cards left in the deck. So there are 4 kings. Did it again. There are still 4 kings, but there's only 51 cards. What if it had said jack instead of king? So pick a jack and then another jack. Then it would have been 3 out of 51. So you're seeing how this could vary, right? All right. What is it? I'll trust you. What do the calculators say on that one? 4 out of 663. And if I remember right, it's basically the same decimal percent. Is that right? 0.0 or 0.6. That's okay. 0.6. All right, that was learning target 4. What did we do every time? And was multiply. Flip it over, learning target 5. It takes a little more explanation. Learning target 5 are OR problems. Calculate the probability of mutually exclusive and non-mutually exclusive events. So 2 new vocabulary words. For OR problems, you will add always and sometimes subtract. Add and sometimes subtract. Let's define the new vocabulary. Mutually exclusive. That is 2 events that cannot happen at the same time. So let's use the deck of cards. If I'm drawing 1 card out of that deck, can I get a jack and a king at the same time? If I'm drawing 1 card, can I get a jack and a king at the same time? Then those are called mutually exclusive. Now let's look down here. Non-mutually exclusive. 2 events that can happen at the same time. Can I draw 1 card out of a deck and get a jack that's red? Can you get a jack or a red at the same time? You sure can. Jack of hearts, jack of diamonds. So do you see how that can happen at the same time? That's called non-mutually exclusive. So look at the 2 formulas. How are they alike and how are they different? What's alike about the 2 formulas? They both have addition. You're both adding the probability of A to the probability of B. But then in the non-mutually exclusive, you have to what? Subtract the probability of A and B. It'll make more sense once we define an A, call it something, and call a B. It'll make more sense later, okay? But for the first 2 problems, just use the formulas. For 8 and 9, use the formulas. You try it. Number 8. They are mutually exclusive. So find the probability of A or B. The formula says add the probability of A to the probability of B. 1/6 plus 1/3. You can do it in your calculator, or 1/3 is 2 out of 6. And if you add 1/6 and 2/6, you get 3/6. You get a half. So 1/2, 50%. Everybody agree on that? Is that what you got? Okay. Non-mutually exclusive for number 9. You add them still. Yeah, you still add 1/6 and 1/3. But according to the non-mutually exclusive formula, you're supposed to subtract the probability of A and B, which in this problem is also, it's just a coincidence. It's also 1/6. So subtract 1/6. So what do you get? 1/6 plus 1/3, but then minus a 6. Those cancel, don't they? You're left with 1/3. Or about 33.3%. All right, now let's put some A's and B's. Let's call them something. It'll start making more sense. Deck of cards. Using a standard deck of cards, you pull one card out. State whether the events are mutually exclusive or not, then find the probabilities. So the task that I want you to do first is go through 10, 11, 12, and 13 and tell me if it's M for mutually exclusive or NM for non. Start with 10. Is it mutually exclusive or not? Can you draw one card and get a king and an ace at the same time? No, that can't happen. So 10 is M. Use that test on each problem. Number 11, a king or a red. Exactly. At the top, mutually exclusive. It can't happen at the same time. King or red, can that happen at the same time? Are there any kings that are red? Then it's non-mutually exclusive. The definitions are at the top of the page, right? If it can happen at the same time, it's non-mutually exclusive. Exactly. Yeah, you're just drawing one card. So what about 12? Heart or spade? Yeah, it's mutually exclusive. Very good. What about heart or red card? What's that? NM, like non-mutually? Yeah, because that can happen at the same time. Perfect. Let's do, yes. There is no card in the deck, we'll look at number 10, that has both the letter K for king and the letter A for ace. Another example, number 12. There's no card. If I pull one card out of the deck, number 12, it cannot be both a heart and a spade. Have you not played with the cards much at all? All right, well, then I'll bring a deck of cards in and show you. They are labeled king of hearts or king of spades. Different cards. Yeah, I could pull up solid. Well, I don't know if the district will allow me. If I can pull up, I don't even know if games are in here. No, Games Explorer, I don't want to get into something like that. So, but I'll bring in a deck of cards and show you so it'll make a little more sense. But no, there's no card that's both a heart and a spade. All right. So now back to number 10, find the probability. It's an or, so you're adding. What's the probability of getting a king? 4 out of 52. What's the probability of getting an ace? 4 out of 52. When you add those two fractions, you get 8 out of 52, which reduces 8 out of 52 to 2 out of 13 and about 15.4%. So 2 out of 13 and about 15.4%. All right, let's skip number 11. Let's go to 12 because it's the other easy one. Heart or spade? So start with the probability of a heart. 13 out of 52. Spades, 13 of them out of 52. It also might make sense this way. Hearts or spade, that's 2 of the 4 suits. That's half the deck. 26 out of 52, which reduces to 1/2 or 50%. All right, now it kind of gets a little bit tricky. So I'm going to start number 11 by writing it using the symbols. The probability of a king plus the probability of a red minus a probability of, well, let's think. In the formula at the top, it says A and B. What is a king and red? A red king. A red king. Agree? A red king. A king that is red. That's going to be two of them. All right, so now let's find all those three probabilities and add and subtract accordingly. Kings, 4 out of 52. Oh, that 4 is getting me every time. 4 out of 52. Reds. That would be diamonds and hearts, right? Diamonds, so it's 26 out of 52. Minus the probability of getting a red king. How many of those are there? How many kings are red? The king of hearts and the king of diamonds. 2 out of 52. When you add those fractions and then subtract 2, you have 4 plus 26, 30, minus 2. If you do it in the calculator, you're going to miss this. You're not going to make this connection. Calculator is going to spit out a reduced fraction. But look at my answer, 28, and think about this. This is where it really makes sense. This is where you start to really say, oh, I get it. Oh, I get it. What is that for? What cards are those for? King of hearts, king of diamonds, king of spades, king of clubs, right? Look at the 26 out of 52. But what is that 26? It's all the red cards, right? Would you agree that that has king of hearts and king of diamonds in it? Then that means you counted them twice. If you have 4 kings and 26 reds, you're counting the king of hearts and the king of diamonds in both of those fractions. You counted it twice. That's why you have to subtract those 2 red kings, because you counted them twice. Kind of makes sense? Here's another way to do this question. Go back to yesterday's definition of probability. Count your successes over total possible. You ready? The 4 kings. The 4 kings. And don't add 26. Add the 24 red cards that you haven't already counted. And then you don't have to do any subtraction. See the difference? Now, some of you, I can see the light bulbs going off. All right? We'll do a few more, and I think the more we do, the more light bulbs will go off, all right? But I'll trust you. What's the reduced fraction on that one? 7 over 13 and percent? 7 over 13, 50, what'd you say? 53.8. Gotta get better with my penmanship. All right, last one in this set, 13. The probability of getting a heart or a red card. We already said that that is a non-mutually exclusive event. So we need to add 2 fractions and subtract something. All right, so hearts, 13 out of 52. Plus the probability of red cards, 26. Now I'm going to stop before I even write another number. When I write 26, what is it representing? The hearts that I already counted and the diamonds. I am essentially counting the hearts twice. So now I've got to subtract the probability that it's a heart and red, which is all the hearts. Subtract 13 out of 52. So what was that, Luke? So you could just, when I wrote 26 there, think about it and not write 26. Just write 13. Don't count the hearts twice. But either way you get there, that's a half. That's 50%. All right, but I want to make a little side note. Don't start skipping the formula every time, because some questions on the test, the quiz, the EOC, the homework, you have to know the formula. But on a question like this, no, you can get the answer without using the formula, okay? All right, last 4. We switch to number cubes, to dice, instead of cards. What can you get when you roll dice? You can get a 1 and a 2 on the other die. You can get a 3 and a 5. You can get a lot of things, can't you? Yeah, we're switching to number cubes, which is what a dice is. You can get 6 items on one dice. You can get 6 on the other. Fundamental counting principle says 6 times 6, you can get 36 outcomes. What are they? Here they are. When you get it might help if you view the dice as colored. One's red, one's blue. When you get a red one and a blue one, what's the sum? 2. When you get a red 2 and a blue one, what's the sum? All right, so if you'll look here, how many sums are in this chart? It's a 6 by 6 chart. It has 36. So our fractions will be not out of 52 like the deck of cards, out of 36. All right, so let's go back to the notes and let's do them one at a time together. Number 14, is it mutually exclusive or not? What's the probability of getting sum that's 5 or even? All right, so look at the answers. Here are the outcomes. Can you get a 5 that's also even? No, you can't. So this is mutually exclusive. So 2 fractions and add them. So let's go back. All right, the sums, I'm sorry, the 5s, there are how many? 4. So back to the Word document here. 4 out of, all right, I'm just going to write over that 4. 4 out of 36. Evens. Close that if I can. 4, sorry, evens. There's, I'm going to switch ink pen colors if I can. I don't know if it'll let me. I think I can. All right. There's 2, 4, 4, 4, 6, 6, 6, 6, 6, 8, 8, 8, 8, 10, 10, 10, 12. That was 18, wasn't it? That was 18. So 18 out of 36. You will have to list that outcome yourself, yes. On the board to your left, until this period, I didn't even think about it, that I could make an Excel file and do this for you up here and record it on the video. So I've been doing it on the board. But yeah, you'll just have to list out that sample space. Okay. All right, and then when we add those, we get 22 out of 36. Reduces to 11 over 18, or approximately, first person that can tell me, 61.4, 61.1. Is that what y'all got? 61.1. All right. Now, number 15. I got to go back to my Excel file here and erase all that and start over. All right, so not sum is 5 or even, but sum is prime or even. Prime or even. Prime or even. What's prime number? 7's prime. 5 is prime. 9's not because it's 3 times 3. Are you remembering that definition now? Prime is any number that is that the only factors of that number are 1 in itself. So 2 is prime, 3 is prime, 5 is prime, 7 is prime. Whoops. 7 is prime. 8's not, 9's not, 10's not, 11's prime. Those are your primes. How many numbers? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's 15. So 15 out of 36. All right, now, I'm doing this on purpose. Let's see. Don't tell me it froze up. Let's see if this works. Looks like it's still recording. All right, so maybe we got lucky. The prime numbers, there were 15. So we'll go back to the Word document, 15 out of 36. Plus the even numbers. So let's see, evens. Oh, now watch what happens. Watch what happens. Switching colors. What just happened on that 2? I circled the 2 twice. I'm still circling evens, though. I circled 18 things with the black marker, 18 evens. I circled that 2 twice. So there's 2 ways to finish this question. Option 1 is there were 18 evens. And if I count all 18 of them, I've got to subtract anything that was prime and even. So that was the 2. Prime and even, that was the 2 I circled, so subtract 1 out of 36, or don't count it twice in the first place. Does that make sense? Don't count it twice in the first place, or that literally is what the formula would say, subtract the primes that are even, prime and even. So 33 of them minus 1, 32 out of 36. So I'll do that on the calculator. I'm running out of room. So 32 divided by 36, math, enter, enter. That would be 8 out of 9, or 89%. 8 out of 9, or 88.9%. All right, I'd like for you to try the next 2, even or greater than 6. I'll put the document up here and give you a second to look, and I'll copy it over here. What does it say? Even or greater than 6. All right, so you can kind of, fingers and toes, count them up. How many evens? 18. Half of them are even, half of them are odd. That'll help you with the evens from now on. So 18 out of 36. Greater than 6. Is 6 greater than 6? No, so don't count the 6s. Now, I see you pointing and counting in your head. I'm curious. Are you counting the 7s, 8s, 9s, 10s, 11s, and 12s? That's fine if that's what you're doing. If you're counting the 7s, 8s, 9s, 10s, 11s, 12s, and you get what? You get 20, 21, 21? That is fine. Nothing wrong with that. But here's what just happened. You just counted anything that is even and circled twice. You counted all those twice. You counted all those twice. You counted that twice. So you've got to subtract anything that is both even and bigger than 6, or don't count it twice in the first place. Make sense? So 1, 2, 3, 4, 5, 6, 7, 8, 9. You counted 9 of them twice. That is the evens and greater than 6. So when you add all that up together, you get 39 minus 9. You get 30 out of 36. Now, I'm going to erase everything and start that problem over. And all I'm going to do this time is circle anything that is even or bigger than 6. Evens. Evens. Got it. Got it. Evens. All right, now what else am I going to circle? Anything else that's or greater than 6. 7s, the 9s, and the 11s. How many circles is that? Probably would be easier to take the 36 and subtract the ones I didn't circle. 30, isn't it? So do you see how you can get to this answer either way? Using the formula, or just use the definition of probability. Count your successes and count your total. All right. What does that reduce to? 15 over 18. So 5 over 6, which is about what percent? 83.3. All right. I'm going to clear the last one. Sum is even, multiple of 3, and let you do it completely by yourself. You choose the method. Sum is even or multiple of 3. Sum is even, multiple of 3. Yes, they are. All of the numbers on that chart in the middle are what you get when you add the outcomes on the die. So what we say is even or a multiple of 3. Fairly certain you're going to do all the evens that way. So we'll start there, and then you finish it off. So how are you finishing it? Are you counting all the multiples of 3? Are you counting all the multiples of 3 that you haven't already counted? The multiples of 3 are these numbers: 3, 6, 9, 12, 15, 18, and we're already past our list. That's multiples of 3. 3, 6, 9, 12, 15, 18, 21, 24, and 6s. Okay, so it sounds like to me you're wanting to go with this method. When you circle the multiples of 3, circle the 3's, but don't circle the 6's again. Circle the 9's, but don't circle the 12 again. This is fine, okay? It is okay for you to do these problems this way, but don't forget the formula for when you need the formula. So 1, 2, 3, 4, 5. How many is that? First of all, students, if you've lost something lately, 24 out of 36. That is located next to the ink machine down by the cafeteria.